All right, hi everybody, it is Miss Thompson. We are going to talk about function transformations. This is topic 1.5 from our first unit, and we did a lot of this in class, so I'm going to quickly go through and just give you these formal rules. So we're talking about horizontal shifts, vertical shifts, horizontal squeezes, and vertical stretches. I had to remember what my word was. That has to be changed. All right, let's start with horizontal shifts. Horizontal shifts is when we move a function left. So we just move left or right. So just left or right, so our function goes this way or our function goes this way. And it's important to note that this does not change the size. So we'll add down here. Does not change the size or shape. So my function stays the exact same size. So one example of this is I could move this function to the left, which would go this way, and my function would stay about the same width and the same size and height, but it would shift in that direction. And another example is my function could shift all the way over here to the right, and again, staying about the same size and width and height, but just moving left and right. That is called a horizontal shift. And when we do this by adding or subtracting within our parentheses, so in our input. So we're adding or subtracting to the input. And a negative c moves our function c units to the right. Ooh, to the right. Sorry, this way is right. So minus c moves c units to the right. So it's kind of backwards. When you have a minus c, you go right. A plus c, you go left. A little backwards than usual. So this might be, for example, f of x plus 3. I'll write that here. That might be f of x minus 3, sorry. And my red one, on the other hand, might be more like f of x plus 2. Those are two examples I could get. All right, vertical shifts. Vertical shifts move instead of left or right, they move up or down. And again, we are not changing the shape or size. Not changing the shape or size, the same size and shape. So an example of this, we could have something go up, same size, same shape, just shifted upwards. Or we could also have something come down like that. So we have an up and we have a down. And we do this by adding outside of our input. So we're adding to the function as a whole. So this is the thing that we're adding. And what this does is it moves d units up. D units up. So positive in this case moves upward. So this graph over here might be f of x plus 4 could be what it is. We're going 4 units up. Whereas my blue graph might be more like f of x minus 3. Oops, extra parentheses there, minus 3, but it moves it down. All right, we've also got horizontal squeezes. Horizontal squeezes essentially squeeze narrower or stretch wider. So I think of horizontal squeezes being this way or this way, pulling in or pushing out. These guys do change the shape or size. They do change the shape or size. So one example of this is if we squeeze narrow, we might end up with something like this. And you'll notice that it's the same height, it's in the same location, but my sides have squeezed in towards the center. Or I can end up with one that gets wider, like this, where again, the same height, but I've pulled and stretched my function outward. So this, we say, is we multiply inside by our input. So this b is the thing that gives us a horizontal squeeze. And what it does is it squeezes by a factor of b. Squeezes by a factor of b. Now this is multiplicative in nature, and so if I'm squeezing by b, that might mean, for example, I'm just going to add, or I'll just put it on the blue one here, that this might be something like f of 2x, because I've squeezed it by a factor of 2. So in this case, b being bigger than 1 makes it come in closer. And this one out here might be more like f of 1/2 x, because I'm stretching it, so it's going to be the opposite. One note I'm going to make here is that if b is less than 0, I get a reflection. I get a reflection this way. So if I've essentially squeezed it all the way through, I'm going to reverse my graph and end up with a reflection. My last one down here is a vertical stretch. So similar to horizontal squeeze, a vertical stretch is going to stretch taller, because this is vertical, or squeeze shorter. So we're going to stretch it taller or squeeze it shorter. And I call horizontal a squeeze and vertical a stretch, because when b is bigger, horizontal defaults to getting thinner, squeezing, and vertical defaults to getting taller. So they kind of do the opposite. So a vertical stretch is going to leave my width the same, but it's going to make my function taller. So it kind of stretches it up like this. Or it's going to leave it the same, but make it shorter. This is the same width, but my height can be halved. This is done by multiplying by a number on the outside, and it stretches by a factor of a. So here we've got this big blue function. This got taller, we'll say by double. And so this might be 2 of f of x. Whereas my red function got shorter, so I might call it 1/2 f of x. And it's worth noting that if a is less than 0, if a is a negative, I'm actually going to stretch down into our negative. So I get a reflection. This is where our reflection comes from, and it's an up-down reflection. So for example, what I might end up with is something like this, where it's flipped over and it's stretched out a little bit. All right, so lots of examples of these online. Really your goal is you want to be able to remember what each of these rules does. So minus c next to x is a horizontal move, plus d is a vertical move, and then b and a are stretches, b in the horizontal direction, a in the vertical direction, and we're going to want to be able to identify those independently on a graph.